So we start another new topic, simple harmonic motion, often abbreviated to SHM, and you might hear the phrase or the term simple harmonic oscillator. Before we look at what a simple harmonic oscillator is, let's go back a little bit and link what we understood or what we've learned about waves and circular motion and oscillations previously, so that we've got a good grounding to learn about simple harmonic motion in the next lesson. So an oscillator is something which moves backwards and forwards with a regular pattern. Waves, for example, are oscillators, or the things that make waves are oscillators, and you learnt about those earlier in the year. We use this simulator quite a lot for this topic, and you'll see there's a mass on a spring oscillating up and down with a regular time. It's known as a free oscillator. There's nothing driving it externally. There's an external force to displace it in the first instance, but once it was released it was oscillating itself with internal forces. Let's look at that in more detail and see how it links to waves. So to start off with, I've displaced this. The dotted line is the equilibrium position where the mass would naturally hang if released. I've got a timer, and every 0.1 of a second I'm going to plot a point where the centre of mass of the 100 gram mass on the end of the spring is. So we'll start at time 0 and we'll flick through. We're starting to see a pattern, some sort of shape we might recognise, and of course we get a sine shape, or in this case an inverse cosine, because we started by pulling it downwards. If we'd started at 0 here, then we would have had a sine curve. Okay, next then. An oscillation, a single oscillation, is from the equilibrium position to an amplitude, back through the equilibrium to the negative amplitude, and back to the equilibrium. So that's one oscillation. Okay, a single oscillation. It's important you understand that, so we'll watch it again. Full speed and in slow motion. Equilibrium, amplitude, equilibrium, amplitude, equilibrium. Okay, so it has to end up back where it started, going in the same direction that it started. Right, let's define some things. So if we sketch a wave, then put in the equilibrium position, then put in the equilibrium position somewhere across here, then the amplitude would be this distance here and this distance here, because the negative displacement is equal in size to the positive displacement. So those two displacements are the same magnitude. Okay, time period. Again, let's draw a wave, and this direction this time represents time in seconds. Minutes, but seconds normally. The time it takes to go from the equilibrium position to the amplitude, back through the equilibrium to the negative amplitude, and back to here. Back to here is the time period. And you should remember that the frequency, which is the number of waves per second, is equal to 1 over the time period, and the inverse of that, the time period, is equal to, don't know why I did that, 1 over the frequency. How does that link to circular motion? Let's review what we learned about circular motion. So if I put a horizontal line here, I'm going to measure my angle theta from that horizontal line. This disc is rotating, so this line, this radius, will move around over time. So sometime later it will be over here. This angle therefore will increase, and the rate of increase of that angle is known as the angular velocity, and it's measured in radians per second. You should recall that to do one complete revolution there are 2 pi, symbol is omega, so in one complete revolution it's 2 pi radians, and that takes the time period to get around. But because 1 over the time period is equal to the frequency, then that's also true. Angular velocity is equal to 2 pi f. How does that link then to waves and oscillations? So if I plot this height here over time, then we get a pattern we recognise. So you can see a very clear sine wave forming there. Put the green line in at the end just so you can see that I'm not cheating. Play that again. So why is it a sine wave? Let's have a look. So again, if we're drawing this horizontal line here, well, if that's a right angle and that's theta, then this height here, I'll call it O for the opposite side, and this is r, the radius, then we should know that sine theta is equal to opposite side over the radius. So in other words, the opposite side, or this height here, which we are plotting against time, was equal to sine theta times r. And we should also remember that theta is equal to omega t, where t is some time. Okay. So this height, which we've called O, which I've used a different symbol now, but there we go, is sine